All right, so our task is minimum cost spanning tree. So what is a spanning tree again?
Connected, no cycles graph.
Okay, so a tree is a connected graph with no cycles. So a spanning tree is a subgraph of an existing graph that is connected, no cycles, so it's a tree, and the spanning part is that it includes all the vertices of the original graph. Right? So all the vertices of the original graph are included. All right, so will every graph have a spanning tree?
Yeah.
So does that graph have a spanning tree? It has multiple spanning trees, right? What can we do? We need something, let's say if we need all of these edges, and then what do we need here on this part? We could take away any one of them and have a tree, right? That would include all the vertices. So you take away this one, or you take away this one, or you could take away this one. Right? So this graph has multiple spanning trees. Yes. 3 different spanning trees. Again, they might be isomorphic, right? They might be the same if you take this edge or this edge, as far as that goes. But if they were labeled, then they would be different.
So you can't add new edges, correct?
Right, right. And with a spanning tree, we're not, with a spanning subgraph of any kind, we're not adding new edges that don't already exist. We're just using existing edges. Okay, so this graph has some spanning trees. If there were costs or weights associated with the edges, one of those would be the smallest, or there might be multiple. They all might have the same weight, the same overall cost. So this graph, the original graph, has a spanning tree. What about this graph?
Shoot.
Does it have a spanning tree?
Let's stop assuming things are connected.
Right, so for a graph to have a spanning tree, the graph has to be connected to begin with. What happens if it's not connected? Each part would have a spanning tree, each component. So in all, if the graph is connected, there's at least one spanning tree. If the graph is not connected, then we're looking at spanning forests. Right? So each component having a tree. So some of the algorithm we're looking for are for minimum cost spanning tree. Some of these will give you a minimum cost spanning forest if the graph's not connected, and some of them break if the graph is not connected. So some of the algorithms that we're looking at require a connected graph, and some don't. Okay, so we're talking about the situation of, is there a solution to this problem, right? We're trying to find a minimum cost spanning tree. Is there always a solution? Well, it depends on whether the graph was connected or not. If the graph is not connected, there is no minimum cost spanning tree, but then we might be looking for a minimum cost spanning forest. Okay, so the first algorithm that I know of for calculating this is, let's see if I can spell this correctly. Is Borufka's algorithm. It was created in 1926 for the purpose of optimizing the electricity network for Moravia. So it was created to optimize the electricity network, which means what happens? You don't need cycles or anything to get power from one place to another place, right? We don't have to have connections there and connections back, right? We connect there, and so building this connection required a tree. And so what was the idea? They wanted minimum cost because it was actually what is the cost going to be to provide or build out this electricity network. So the cost could be associated with the actual dollar amount or material or distance, whatever, in the different context of what cost can mean. All right, so what happens in this situation is we have a graph to start with, right? So we have a situation and we have the weights wherever we got those, whatever happens. So I'm going to draw a stolen graph.
Stole it?
I stole it. I stole this from Wikipedia.
What if someone changed it and it's wrong? Did you
Well, it
check
doesn't matter. It's just an example graph. It's not the graph that was based on the original problem. It's just some graph with some values in place that is nice for showing what happens with this, with some of these algorithms. Any numbers would work. Any number of vertices would work. It's just big enough with nice enough weights to show the different scenarios. Okay, so we just have a bunch of vertices and a bunch of edges and weights. So this is the structure that we have to start with. We want to work with this structure, and we want to find a minimum cost spanning tree. All right, so this algorithm starts with 12 separate trees. This 12 separate trees is each vertex by itself, so no edges, right? Each isolated vertex. We look at each one of those pieces individually and we say, okay, what is the smallest weight from this tree? What's the smallest thing that I could use to connect this tree to another tree? Right? So we're going to try to reduce the number of components. Well, up from here, the two smallest, or the two options, are 13 and 6 weight. So we're going to add the 6 for that one. We're going to come to here, and we will add the 1. We're going to come here. We add the 6, because that's the smallest one from there, but it's already added, so we're just making a list of it, right? We're saying, okay, that will be the smallest one. What's the smallest from here? Is 1. Smallest from here is this one. Smallest from F, that one again. Right? So we've only actually added 3 new edges. Not adding 3 new edges, adding 3 edges to the spanning tree, right? Marking them as being part of the spanning tree. Does that make sense? So what also happens is now we're going to mark these two as being part of the same tree. These 2 vertices are part of the same tree. These 2 vertices are part of the same tree. But now we have to finish off and look over here at the graph. So G, what's the smallest? That one. H, that one's the smallest. I, that one's the smallest. We're okay there. J gives us this one. And K gives that one. And L duplicates that one again. All right. So that's round one. We've gone through all of the individual trees, and we have connected each one of those to something else. Okay. So now then, we're going to look at this component and look at the edges from that component to other components. So we have this edge, this one, all of these edges to consider that go from this component to other components. And we want the smallest one of those. So what happens? The smallest weight from this component is this one.
Wait, can you repeat this second part?
So we're doing the same thing again that we did where these were individual trees, but now this is the tree. So we're looking at all the edges that leave this tree. So we have a 13, a 7, a 14, an 8, and a 20. And we're taking the smallest one of those.
So we're treating A and C as like one.
So A and C is now one tree.
Okay.
Now we're going to do the same thing with BD. What's the smallest weight out of there? Well, there's a 13, a 7, a 14, a 9, and a 3. Right? These are the edges.
Well, a 3.
So we're going to take the 3 at this point. This tree EF, the weights going out 3, 9, 8, and 18. So we would mark this one again as being for inclusion. But again, we're only adding it one time, but it got selected on this end and it gets selected on that end. But it's like setting the flag that says, this edge included, true. And then over here we said, this edge included, still true. All right, now we come over here. We have a tree right here and a tree here. So let's look at this tree. What edges leave this tree or connect this tree to something else? 20, 16, and 12 weights. So which one do we select? We select the 12 weight. And then we're looking at this tree, and we have 12, 16, and 18. And so the 12 just got marked twice, and that's the one that's included. So what happens after our second pass through the algorithm? We have a tree here, and we have a tree over here. So now there are two components. Now we're going to look at the edges from this component. Right, so these edges that are in here don't go between different components. What would happen if we included any of these edges? If we included any of these edges, we would have made cycles. Right? So none of these edges are under consideration. We're only considering edges between a vertex in one component or in one tree and vertices in a different component or tree. So over here, what happens? If you include this edge, you get a cycle right there as well. And that's the only edge that's inside. So what edges do we have actually to consider? These two. These are the only two edges to consider. We take the smaller one. Right there. And there's our tree. Okay, the tree that we're looking at is all of those pieces, right? The ones that are in some color. The blue ones were in the first round. The red ones were added in the second round. I think, is that the order, or was it the other way around? Yes, red ones were second round, and then that green edge is the third round. Now what do we have? How many components do we have? How many trees do we have?
One.
We have one tree, and it's spanning because it includes all the vertices. So when we get down to one tree, we're done. Now what could have happened instead if the graph had not been connected? What would have happened? There wouldn't be any edges left between the components, and we would have built, instead of a minimum cost spanning tree, we would have built a minimum cost spanning forest. All right, so what kind of algorithm is this? This algorithm is an example of a greedy algorithm like we talked about before. What are we doing at each step? At each step, we're picking the best possible answer that's available. Can that ever come back to hurt us? We have connected A and C with the cheapest possible link that exists between A and C. There's no way to do it cheaper, so it's never going to end up hurting us later because all we need is a connection between them. We don't need to worry about, oh, that might force us later to choose the 13, or doing something might force us later to choose the 20. No, we don't have to choose the 20 because making the best choice now can never force us into a bad choice later on. We just keep making the best choices. Does that make sense? All right, so this algorithm it does this in this greedy process, but starts with everything separated and builds toward a single spanning tree, or if the case requires it, builds toward a spanning forest, right? But it will be minimum cost, and there's proof involved, but it will be minimum cost because we're always making the best choice possible, and making a good choice now can never force us to make a bad choice later on. What if we make a bad choice now? There would have been a better choice, right? If you pick something that cost more, well, that means there would have been a better choice that was available, so what you create wouldn't have been minimum cost. So you never want to make a bad choice now. You always make the best choice now, and then it can never hurt you later on. Okay, so this algorithm from 1926 was used to try to find the most efficient way to build an electrical network.
Can a graph have more than one minimum cost spanning tree?
What if this weight right here had also been 18?
Guess we would have had two.
Right? If this had also everything else exactly the same, but this had also been 18, we would have had to have some tiebreaker decision here, which one to choose, and we could have had this one or that one, and they would have had exactly the same cost. So certainly, more than one is possible. They will all have the same cost, right, being the minimum, but there could be more than one. There could be lots. I mean, what happens if all the weights are just one? Then whichever spanning tree you find, right, you have there's going to be lots of different minimum cost spanning trees in that case. But even in something like this, if these both happen to be the same cost, or some other adjustments, right, something over, you can see situations where you could have multiple different spanning trees. Okay, so this algorithm was the first one, at least the first one that I know of that was published. 1926. Okay, so what I should have done was make copies of this graph so we could apply other algorithms to it as well. I guess I can move the color away, and we can apply the other algorithms on the same picture. Borufka's algorithm, and if we analyze this, we have to go through some work, but you can create this, let's say log is really log base 2. In terms of big O notation, or really, so big O because of the worst case scenario here, right? This is the worst case. That this algorithm might take the size times the log of the order, right? The number of edges times the log of the number of vertices. So big O of that is like the worst case situation for this algorithm. Now what happens? What do we have to keep track of? What do we have to do in all of this? We have to be able to keep track of which edges are the least weight, the minimum weight. We also have to keep track of which components we're talking about, right? So how do you tell that things are in the same component? How do you then, when you have a component, how do you find the minimum weight out of, or that is adjacent to that component? So there's some work, and we have to be careful in how we remember all of this. But what could we do at the beginning? Each thing is in its own component at the beginning, right? Its own tree. When you find an edge and you connect two things, then we can label both of those, and we can record this as being in the same component. So then every edge that's adjacent to this and every edge that's adjacent to that are in the same, or then correspond to things coming from that component. So we can see if we were building these components and keeping track of that data as well, right? So component class or something that has that kind of information in there. So things can change classes when they're connected to one of the other components. So one component then becomes part of a bigger component. So it's all one piece at that point. Okay, so the worst case here, unless the graph happens to be a planar graph, and then there's a linear time ways to speed this up if the graph is a planar graph. Remember, a planar graph is a graph that can be drawn so that no edges cross. So it might not be drawn that way, but it can be drawn that way. This graph already has no crossing edges. And so there are ways to speed things up in certain situations. All right. So that is Baruch's algorithm. Let's see. Oh, don't want to take that part. Move that. Let's take that away.
I pick up sticks.
All right, our next algorithm that we're going to look at is Kruskall's algorithm. Kruskall's algorithm is from 1956. And the idea here is that we are going to start adding in edges of minimum weight until we can't do it anymore. All right, so we're going to think of all of these edges in terms of maybe putting them in order. And say, okay, which edge has the minimum weight? That's this one. So we're going to include that one in our tree. That's the cheapest connection between B and D that's possible. So we're going to use that. We're going to utilize that connection. What's the next cheapest weight? This one. We're going to add it. What's the next cheapest weight? So what are we really thinking of? We're starting with a whole bunch of different trees, right? Independent, isolated vertices. And then we're going to start connecting the pieces. All right. Next one is here. Next smallest weight is here. All right, let's think about what's going on while we're doing this. How many edges will we have in a spanning tree for this graph? There are 12 vertices. How many edges?
11.
We'll have 11 edges. So once we get to 11 edges, we can stop, right? Since the graph is connected at this point. But let's keep going. So what's next? 6 is next.
7.
And 7.
Oh, wait. Uh-oh.
What about 8?
You can't do 8.
Can't do 8 because 8 would create a cycle. So we skip over 8. What about 9? We create a cycle, can't do that.
10's okay.
10's okay.
It's kind of rude, there's no 11.
There's no 11. 12's okay.
13's no go.
13's no good. 14's no good.
15's alright.
15's in.
Let's just jump straight to 18.
16's bad. And 18's good. And what tree do we have?
The same one.
Exactly the same tree as last time, right? Because this graph has one minimum weight or minimum cost spanning tree, and it's that one. Does that make sense?
So for each, before you were writing this algorithm, before you could actually pick the edge, you'd have to look at that vertice and its, I guess, tree or graph to see if it can get back to itself, to see if there's a cycle. in there.
Well, so we could do the same kind of thing. You could record which component that it's in. So we could record that this vertex is in a component, and this vertex is in the same component, so we can't add an edge between two things that are in the same component.
Gotcha.
So that's one way to keep track of it. The other way to keep track of it is to try to find a path between them. If there's already a path between them, then don't add that edge.
Mm-hmm.
But doing that is going to be a lot more work, because each time you're trying to figure out, okay, can I add this edge or not? If we can record, oh, this is now part of this component, this is now part of the same component, all right, we don't have to consider that edge anymore. Right? So anytime we add an edge between things, we could mark them as being in the same component. And then anything that edge has been added, or anything that gets added to that later, all of them are now in the same component, and so on. Does that make sense? And we never have to add the edges or check anything on edges between two vertices in the same component. Okay, so this algorithm in the analysis also takes that much time. The analysis actually gives it in the context of big O of, this is wrong. Actually gives it in the context of big O of the size times log of size, but it turns out that the log of size, since the size is big O of the number of vertices squared, remember how many edges there could be in the worst case? The number of edges in the worst case, n times n minus 1 over 2 edges. So that is, this is still, the number of edges is big O of the number of vertices squared. So log of that, we can replace the E with the V. You get a different coefficient, but it still turns out to be big O. I should have changed marker size here. With different coefficients, but big O doesn't care about the coefficients, right? Okay, so Kruskall's algorithm, again, starts with separate pieces and then glues them all together until you get to the end when everything becomes one. All right. Make sense? Oh no. Oh, please. Yeah, there's lots more. Kruskall's algorithm was published in 1956, and with it was like a 2 or 3 page paper. Was another algorithm called reverse delete algorithm. And in that one, reverse delete, you start with the whole graph like this and delete things in highest weight that don't create more components. So everything in this case, we check it and it's connected, so everything is one component, and we start deleting highest weight edges that don't create new components. So it's exactly like Kruskal, only in reverse. So that's why it's called reverse delete, right? So it does exactly, and it gives you the same tree at the end. We're not going to go through that example, but it is a different algorithm, and it has some takes some extra work in order to determine are things still in the same component, have the components gone up. But in that case, reverse delete, it turns out to be big O of the size times log of the order times log of the order cubed. All right, so what happens? What's log of log? That's a very small number, right? Log of something is smaller than the number itself, but log of that is even smaller. But there's the portion of that algorithm, and then there's the part that corresponds to the extra bookkeeping that's necessary. So reverse delete is sometimes easier to conceptualize, but there's more work involved. All right, so we're not going to go into detail on that one. The next one we're going to talk about is Prem's algorithm, except it shouldn't probably be called Prem's algorithm. Prem came up with this in 1957, but Yarnik had already come up with it in 1930.
She stole it.
So Prem was 1957, and then Dijkstra published it in 1959. Now the thing was, at the time, people didn't necessarily know what other people were doing, especially things written in different languages and so on. So, and sometimes people weren't working; they were working for corporations, and so things were internal and weren't released and so on. So sometimes this is called the Prem Yarnik. I don't know if that's how you pronounce that. I don't speak Czech. Sometimes some people call it DJP to give them all credit for it. Lots of English language things tend to call it Prem's algorithm still. All right, so what happens in this algorithm is we're going to start from a particular vertex. This is some arbitrarily chosen vertex. All right, so which vertex do you want to start with?
E.
E. All right, so we're going to start with vertex E. And we are going to build a tree from E. So from E, what is the smallest weight that we want to include? Well, the smallest weight from E is this one. Now this is our tree. What's the smallest weight out of this tree? 3, so we're going to include that one. From this tree, what's the smallest weight out? This 1. From this overall tree that we have now, these 4 vertices, smallest weight? 7. Now from this bigger tree, smallest weight out of it. Again, we don't worry about the ones that are inside between adjacent vertices or between vertices that are part of the tree. We're only looking at the ones to the outside. That gives us the 6. So we've built this side. So this is a tree for that spans this portion of the graph. All of these edges are internal, right, between vertices that already exist in the tree, so we don't look at those anymore. We look now, what's the smallest vertex out of the tree? Or the smallest, not vertex, smallest edge weight out of the tree is the 18. So we connect there. Now here's the tree. Smallest edge weight out of that tree is here. And then we get that one. Then we get that one. Then we get that one. And finally, we get that one. And again, which tree do we build? Same tree, because there's only one minimum cost spanning tree in this graph. If you had choices, there would be tiebreakers of how you decide which choice to make, alphabetically or whatever choice you make, right? Some way of breaking the tie if the 2 values were the same. Okay, what happens with this algorithm if the graph is not connected?
Just finds the minimum cost spanning tree for that little chunk.
Yeah, so whichever vertex you started with, it will find a minimum cost spanning tree for that piece, but it won't find anything for the other pieces, right? So it won't find a forest if the graph is disconnected, but the other 2 algorithms will find a minimum cost spanning forest, even if the graph has multiple components. But this one doesn't do that. But what does it do? It builds one tree from start to finish. So we're only connecting edges to the existing tree. Rather than building a bunch of separate trees, building a forest and gluing it all together at the right time, this just builds out from one tree. But again, what's going to happen? We're only picking the cheapest way to connect pieces, so we're never going to later find a cheaper way. Right? If there had been a cheaper edge at some point, then the tree would have grown in a different way and eventually would have covered everything if the graph is connected. So Prim's algorithm, the complexity completely depends on how we represent the graph, represent all the pieces. We haven't talked about this yet. I think we maybe have mentioned it. If we use an adjacency matrix, an adjacency matrix is a square matrix of zeros and ones. The entry in the matrix is 1 if the edge exists, or we could put the weight of the edge there in some cases. But it's typically, as a binary matrix, the entry is 1 if there's an edge, and it's a 0 if there's not an edge. So let's just look at a small portion of this adjacency matrix. Let's just look at the ABC part of an adjacency matrix. There aren't any loops, so we have zeros on the diagonal. There is an edge between A and B. There is an edge between A and C. And so since there's no direction on it, that's symmetric. And there's an edge between B and C. And so likewise between C and B. So that's the corresponding adjacency matrix for that little component. Right, not component, that little portion, that subgraph of this graph. But then it's the whole thing, right? So what's going to happen in here, there's going to be lots of zeros because these things aren't adjacent to those things. So lots of zeros. And what could you do? We could pare this down. Since it's symmetric, we only need, say, the upper half of the matrix. Not even the diagonal part, so we only need the upper portion, or the lower portion correspondingly, whichever one you prefer. So with an adjacency matrix, then what could we also include rather than just the ones? We could include the corresponding weights, because those weights then could replace the one. If there's a number there, then there's an edge. Except in a situation where in real life scenarios you might have weights that could be zero. So you could imagine some kind of thing where it wouldn't cost you to ship something from one place to the other because you can put that on a truck that was going there anyway or something, right? So these are dealing with positive weights. What would happen if you had negative weights? Well, we won't talk about that right now. We'll talk about that later on when we're doing pathfinding kinds of things. Could you ever have, if say this was the cost of something, what would a negative weight correspond to?
Like on those like extreme couponer shows where they have so many coupons that the grocery store owes them.
Yeah, right? So you could make money on something. Rather than it cost you money, you somehow figure out a way to make money. Get money back from okay, so negative weights sometimes have their place. But in this algorithm, if you're using the adjacency matrix, then worst case is there. We can do better in some cases. If we use a binary heap and an adjacency list, so if we use a binary heap and an adjacency list includes what is adjacent to this vertex, what's adjacent to this one, what's adjacent to this one. So it's kind of a similar idea, but in a different way. In that case, we end up with something a little different. But if we use a Fibonacci heap and an adjacency list, turns out, did you do Fibonacci heaps in data structures? No, okay. We can maybe talk about that. Turns out to be smaller. That's a smaller value. Well, not exactly. We'll have to be careful. Can be smaller if you have sufficiently sparse graph, right? If you have sufficiently small number of edges. What happens if the graph is very dense? This is already on that order, and so this is adding 2. But if the graph is sparse, so sparse means very few edges of the ones that could potentially be there. So what happens, depending on the graph that you have and depending on how you store the data, this algorithm has very different analyses, right? The analysis for each possibility is very different. Some of these methods can be done in parallel much more readily. What do you think about Prim's algorithm? It's building from one tree.
Sounds like it's from the Hunger Games.
Well, so we can think about the idea of which of these algorithms would be more easily done in parallel and which ones kind of need to be done sequentially. If you do it parallel, then what will that do? Multiple machines. the overall actual time can be decreased even if the amount of work doesn't change, right? We can decrease the time. There is, let's see, I've got to be careful in terms of this analysis. This is just rough ideas. We can talk about a little more detail with Prim's algorithm. If the graph is sufficiently dense, we can use a different kind of heap. Instead of like a binary heap, we can use what's called a d-ary heap or a D heap. So on a binary heap, instead of everything just being binary, you could have a fixed number of children from each parent node, right? So it's 3 or 5 or 15, whatever choice you make, and there's appropriate choices for different graphs. So we will. This is just the rough sketch of the idea. We'll go into a little bit more detail on it later on. So with Verufka's algorithm, Kruskall's algorithm, and Prim's algorithm, what do they all do? They're all greedy algorithms, and they all give the minimum cost spanning tree if one exists. The first two give a minimum cost spanning forest if no tree exists. But Prim's algorithm will just give you a spanning tree for the component that your starting vertex was in. So what could you do? You could then start again with a different vertex from a different component and go until there aren't any components, anything that's not part of a component. We can keep track of that. There is another more recent algorithm that we're not going to go into any detail about. But this one is it's a French American. This guy's son is he directed La La Land. So and some other movies. So anyway, there are other algorithms other than these. So more recent things. There are improvements for various reasons, for various purposes, but these algorithms still get used a lot for the original context, for the original kinds of purposes. But with some tweaks, especially in terms of how would you implement in a different kind of in a different environment, right? With much bigger graphs, what's the right data structure to incorporate and use? This same person also invented a different kind of heap called a soft heap. Again, there's a lot of new data structures or relatively new data structures that can change the implementation of lots and lots of algorithms. But for our purposes, what do we care about? We care about the big picture idea right now of we want to build a minimum cost spanning tree. There's lots of different ways to do it. Some of these ways are easier than others to implement. And even if they're not necessarily easier to implement, sometimes the way you implement that algorithm has a big effect on what happens. If we're trying to find the smallest value here, then at some point, since we know we're going to need to find the smallest value multiple times, how we record that information can make a big difference. If we record it in certain ways, then we can always access the smallest really, really easily. It'll always be, say, the first item in the array. Because then once you're done with it, you can throw that one away. But also how we keep track of, are these two vertices in the same component or not? If we keep track of it in certain ways, then it'll speed things up considerably. If we keep track of it in different ways, it will slow us way down, right? We'll have to check again and again. Is it in the same component? Okay. No, or let's add this edge. Later on, are these in the same component? Okay, well, let's check. I mean, if we haven't saved that in a good way, then there's a lot of work involved. Okay, so just very briefly, I want to talk about a function that comes up in the actual analysis of some of these algorithms or their variants. And so before we do that, are there any questions about the ideas that we just talked about? And each one of those algorithms, hopefully, you'll be able to implement. If I give you a graph and say, implement this algorithm, what does it do? Right? So maybe a step by step. We're at this stage in the algorithm, and here's where we are. what happens at the next step kind of scenario, right? We want to be able to follow the procedure. As part of the analysis of these, there's a function that comes up. It's actually not this function, it's an inverse of this function in a particular way. But a function that was created back in the 30s, it's sometimes called Ackermann's function, named after Ackermann, who created it. But the version that we're looking at is a modification of that, which is sometimes, there's an accent on the E, I think it's that way. Ackermann, I guess, came up with this, published his version in 1928. The variation that we're looking at was a few years later, I think 1935 or so. So this is a function with two integer inputs. So these are non-negative. M and N are integers that are not negative. And there's a three-part definition to the function. So we're going to call it A. So if M happens to be 0, then the output is N plus 1. If N happens to be 0, then whatever M was decreases by 1, but N goes up by 1. So M goes down, but N goes up. All right? And then if we had things that are not 0, then it gets a bit more complicated. M goes down. But
oh no, wait a minute.
the second part, the second entry, if recursive or something, gets sometimes much bigger. Okay. So let's see if we can figure out some of the values of this function. Now, by the way, in the analysis of the algorithms that we're talking about, it's not this function that comes up, because this function is going to turn out to have some pretty big numbers involved. It's the inverse of this function. So if you have a function that gets big numbers, what will the inverse get? Small numbers, right? So it's kind of corresponding to exponential and logarithm, right? So, but more extreme. What is put in 0, 0. That's just 1. Right? If you put in 0 anything, what do you get? You get anything plus 1, right? That part's easy. Let's try 1, 0. 2. And what does this become? This becomes this, which is 2. Let's try 1, 1. What happens with 1, 1? This becomes 0.
Which we know is 2.
So we have A of 0, 2, which is
3.
3. We're okay, right? Nice small numbers, not too much to worry about. Let's do 2, 2.
Having trouble. I got to the end, but I'm having trouble like backtracking with the values. My brain hurt, dude.
Can we write a program for this, do you think?
Probably be faster.
Might be faster. We just have to make sure that we get all of the base case conditions just right, right? Make sure we cover all the conditions. We could probably write a program to do this. This turns out to be
You did not just give the answer like that. You
right.
have to prove it right now. Write all that there.
Right? So, but what happens? There's a lot going on to get us there, right? Okay, so we can write down the situation of what happens for certain starting points. For instance, we know what happens again for 0 n, that's n plus 1. If we have 1 and an n, we saw what happens with 1 and an n. We might not have seen this, but we could prove that gives us n plus 2. 2 and an n, just a comma there, 2 and an n turns out to give 2n plus 3. All right, so I mean, and that's what happens right here, right? The n is 2, 2n plus 3 turns out to be 7, but there's a lot of steps to get there if you're working it all the way out. 3 and n turns out to be
I would have expected.
it's like suddenly a major jump.
Thank you for changing.
4 and n
Put down 8 billion.
turns out to be 2 squared squared squared. There are n plus 3 of these.
Wait, what?
Minus 3.
So it's n squared squared squared.
With a total of n plus 3 2's all the way up.
Oh.
All right, so A 4 1.
I can't write the formula on one line. That's just stupid.
Turns out to be, so this is n.
Mm-hmm.
So n plus 3 is 4. So we're going to have like that.
Wait, wouldn't it plus 3
So-
be 4? So, wait.
This is n.
So would there not be?
So there are 4 2's.
Oh, okay.
N plus 3 of those there. So let's see, what do we have? So 2 squared is 4. 2 to the 4th is 16. This is 2 to the 16th. Minus 3. What is 2 to the 16th power?
What is this function used for? I mean, it seems random.
65,536 minus 3. So A41 is 65,533. Big jump. All right, this turns out to have a notation that we use for it. Based on, this is called the Knuth up arrow notation. Saying you raise this to this power. All right, you go bigger and these numbers get really, really, really big in a hurry. All right, so what happens? On one hand, what is this useful for? Well, the inverse of this function grows very, very slowly, and it actually shows up in the analysis of this algorithm we were talking about. On the other hand, what's going to happen with numbers this big? What do you think happens if you try to write a program for it? You're going to have a serious problem unless you have a really good way of handling recursion, right? So it can be useful for testing compilers and so on in terms of what's going to happen with that. It also has a lot of other more theoretical uses in terms of what are the limitations of computing. So we would typically go into some detail about this in automata as well when we talk about at the end of the term what the limitations of computing are. You're not going to see that this term in the automata that those of you are in, and we're not going to see it in the automata that I'm teaching this term. But sometimes we talk about those limitations. We'll talk about those limitations in my section, but not this particular limitation. So anyway, that's just a nice way to go 1 minute past the time. So if you have any questions, let me know. I will possibly post this